This conversation is powered by Google Illuminate. Check out illuminate.google.com for more.
Welcome to this discussion on a fascinating paper, Set-Based Training for Neural Network Verification. The authors propose a novel approach to improve the robustness of neural networks and simplify their formal verification. Let's start with the core problem. What are the challenges in verifying the robustness of neural networks, particularly in safety-critical applications?
The primary challenge lies in the inherent sensitivity of neural networks to even small input perturbations. These perturbations, stemming from noisy sensors or environmental factors, can drastically alter the network's output, leading to potentially catastrophic consequences in safety-critical systems. Formal verification aims to guarantee correct outputs for all possible inputs within a defined range, but this is computationally expensive and often intractable for complex networks. Existing methods frequently sacrifice accuracy for computational efficiency.
The paper addresses this by introducing set-based training. Can you elaborate on how this differs from traditional point-based training methods? Point-based training focuses on optimizing the network's performance for individual input points. Set-based training, in contrast, considers sets of possible inputs and their corresponding output sets. This allows for a more holistic assessment of robustness. Instead of a single gradient, set-based training utilizes a gradient set, providing a gradient for each possible output within the output set.
This gradient set is a key innovation. How does it contribute to improved robustness and easier verification?
The gradient set allows for direct control over the size of the output enclosure. By selecting gradients that point towards the center of the output set, we can shrink the enclosure, thereby improving robustness. Smaller output enclosures also significantly simplify formal verification, as most verification methods become less conservative with tighter bounds.
The paper mentions zonotopes as a representation for these sets. Why are zonotopes chosen, and what are the computational implications of using them?
Zonotopes are chosen for their efficiency in representing and manipulating sets. They offer a good balance between expressiveness and computational tractability. While computing the exact volume of a zonotope is computationally expensive, the paper uses the f-radius as an efficient approximation of the zonotope size, which is differentiable and suitable for gradient-based optimization.
The paper details a novel set-based forward and backward propagation algorithm. What are the key optimizations employed to ensure efficiency, especially in a batch setting?
The algorithm leverages analytical solutions for the image enclosure of common activation functions, ReLU, TON, sigmoid, avoiding computationally expensive sampling or polynomial regression methods. This allows for efficient batch-wise computation on GPs, significantly speeding up the training process. The paper also compares their proposed enclosure method to Singh's enclosure, demonstrating superior performance with smaller approximation errors.
The paper presents an expensive evaluation comparing set-based training to state-of-the-art methods like TRADES, IBP, and SABR. What were the key findings?
The results show that while TRADES achieves the highest clean and adversarial accuracy, its verification is extremely difficult. IBP and SABR offer better verification, but at the cost of lower accuracy. Set-based training provides a compelling compromise, achieving significantly higher verified accuracy than TRADES and better clean/falsified accuracy than IBP and SABR across various datasets: MAssist, CIFAR10, SVHN, TinyImageNet.
The ablation studies are crucial for validating design choices. What insights did these studies provide regarding the hyperparameters and the choice of input sets?
The ablation studies explored the impact of the weighting factor in the set-based loss function, showing a trade-off between accuracy and robustness. They also demonstrated that using smaller input sets, constructed using adversarial attacks, leads to improved performance, confirming findings from previous research. Finally, the comparison of different set propagation methods highlighted the superiority of the proposed image enclosure technique over IBP and Singh's enclosure.
The paper concludes by highlighting the potential of set-based training with gradient sets for robust neural network training and verification. What are the broad implications of this work, and what are potential future research directions?
This work represents a significant step towards making formal verification more practical for neural networks, particularly in safety-critical applications. The ability to directly control the size of the output set during training opens up new possibilities for designing robust and verifiable systems. Future research could explore more sophisticated set representations, improved approximation techniques for activation functions, and extensions to more complex network architectures. The concept of gradient sets itself could also inspire further innovations in robust training methodologies.
This has been a very insightful discussion. Thank you for explaining the key aspects of this important research.